All right, so here we are, the last lecture of the course already. Today's topic is finally neural networks. So neural networks it's a vast topic. It's extremely popular right now, so there's research in every direction, many applications, lots of kind of sub areas. So let's scope this lecture. What are we going to talk about? We're going to think about neural networks as a new hypothesis space. Right? We've had linear models, we've had kernelized linear models, we've had trees, we've had boosted trees. So all these different hypothesis spaces, we're going to introduce neural networks, primarily multilayer perceptrons, a particular type, as a new hypothesis space that has some interesting characteristics. So that's most of the first part of today. So we're primarily thinking about neural networks as a new hypothesis space. And it's a hypothesis space that we'll do learning in using gradient methods. And one thing that's kind of a new challenge with neural networks is that computing the gradient can be quite involved. Sometimes the neural networks are so complicated that it would be essentially impossible to write down the expression for the gradient by hand. That's one side of things. Then there's actually computing the gradient, and if you are naive about how you try to compute the gradient, it becomes kind of computationally intractable. All right, so to introduce some of our notation and concepts, let's start simple, and let's start with linear prediction functions that we've spoken about so many times. So support vector machine, ridge regression, lasso, all examples of linear predictors. Let's start by coming up with a feature vector, 5x, which will denote each coordinate of the feature vector. There's 3 features as a different node in a little directed graph, which we'll call computation graph. So this is a feature vector with 3 features, phi x1 through phi x3. And we're taking a linear combination governed by this parameter w and coming up with a score. If it's a regression, our final product will be the score. If it's classification, we'll map that to a probability or something like that and use a likelihood loss, etc. But the key piece is the score is just this kind of W transpose 5x linear combination of the input features. All right. A neural network adds an extra layer, the basic neural network. We start with the feature vector. And then we have 2 what we call hidden nodes. Each hidden node takes a linear combination of the features and then runs it through this function sigma and produces an output. And we have 2 different versions of that. And they differ in the linear combination that they take of the input features. Right? So we have 2 different, actually affine transformations of the input feature vector. And each of those are passed through some nonlinearity sigma, and they produce output. And then we finally have a affine combination of those to produce the score. This is kind of the simplest, what's called a multilayer perceptron, which is kind of the classical neural network. If we write it down in some equation form, hi, each node hi will be sigma, that's our nonlinear function, of our linear transformation of the input feature vector. We can imagine that there's a bias term in there by setting one of the features to be constant 1 as usual. All right. So this is describing the 2 the 2 hidden nodes, and then finally we'll combine those linearly with some parameters w. So if we put it all together, the final output score is a linear combination of 2 terms. Each term is some scalar times the output of the hidden node, the first hidden node and the second hidden node. Right? So each of these h's, sometimes they're called like computation units. And that's kind of what makes things different from a linear model. So let's talk a little bit. This is kind of the core structure. We can make multilayer perceptrons with different shapes. You can add as many hidden nodes as you want. You can add multiple layers, just repeating the same basic layout. And we'll go into a little more detail on that later on. All right, so one important piece is this nonlinear function. In this context, it's called an activation function. And people use a few different ones in practice. I'll show you the two most common ones. One is the hyperbolic tangent function, which you see graphed here. And another is called the rectified linear unit, which is just like almost like an SVM hinge loss, but flipped and going the other direction. So can you see any reason why you might prefer this tangent function over the ReLU? And then we'll go back the other way, why we might prefer the ReLU over the hyperbolic tangent. All right, yeah?
Hyperbolic is smooth?
Yeah, hyperbolic is smooth, it's differentiable. This seems appealing. We have our subgradient techniques, so we're not scared away by a non-differentiability, but yeah, that's a potential appealing feature. Now how about ReLU? This might have some advantages. Let's think in terms of how easy or hard it is to compute, and how easy or hard it is to compute its derivative. So what's the derivative of this function, say, right here at 0.5?
1.
1. Really easy. So, and the derivative here?
0.
Yeah, so computing the value of the function itself, also trivial. It's just an if statement. If x is greater than 0, we just branch. So computing ReLU and its derivatives is extremely fast, especially compared to tanh. But even that aside, and I don't have any mathematical reason for this, but in practice, ReLU often works better than tanh, just as an empirical thing, and we'll see some experiments on that later. But but this is the choice of the activation function is a hyperparameter, just like all the other hyperparameters we handle. And so in practice, one can try it, different ones. You'll eventually get a favorite. Just use validation to see how they work. If you wanted to, you could use different activation functions in different nodes, although I've never seen that done in practice. Let's do an example that will help expose some interesting properties of neural networks. So as usual, we'll start with regression, which is kind of our simplest example. So regression with multilayer perceptrons. Input space is just reals, one-dimensional, so we can visualize things easily. And action and output space are reals also. So our hypothesis space, we're going to have 3 hidden nodes. And so we can write out the form of the output simply as this kind of affine transformation of H1, H2, and H3. Those are the outputs of our 3 hidden nodes. All right? And so each hidden node has this form that we've talked about before. Now we've explicitly put in the bias term, which turns out to be important. All right, and then sigma, we don't specify quite yet what sigma is. It's some kind of nonlinear transform, probably hyperbolic tangent or ReLU. Okay. So it's just as a concept check, what parameters do we need to fit for this model? What's unspecified? Yeah. Say again?
The weight.
The weights. Okay, great. So we need all the W, W0, W1, W2, W3, the V's, V1, V2, V3, and the B's, B1, B2, B3. So all those we have to figure out. Great. All right, so here's a computation graph describing this neural network. We have one hidden node, it's just a real, one input node, it's just a real value, 3 hidden nodes, and the output. All right. So one way to think about the hidden nodes is as features. So if we were doing a linear model, we would be focusing on this part. So y hat is a linear combination of h1, h2, and h3. If we're in linear modeling, we have to come up with these functions h1, h2, and h3. Those are our feature functions. That's our featurization. So one way to think about a neural network is that it is, in some sense, learning the nonlinear features that we want to create out of X. It's learning them from some parameterized set of feature functions like this. And those features are learned jointly with the final output and the final linear combination of those features. So this should be a little bit reminiscent of what we talked about in gradient boosting regression trees, or we called them adaptive basis function methods, where we had a method to kind of choose the feature function or basis function that we then added with a kind of scalar multiple to our total prediction function. So it has a similar form, same form. Okay. All right. So for the hyperbolic tangent activation function, the feature functions, the HIs, the hidden nodes, will be able to form tanh Vix plus Bi. And what I've done here is I've taken some random samples of the parameters Vi and Bi just to see what types of feature functions we get. And here's what they look like. You'll remember tanh approaches, it never exceeds 1 or -1. And so these feature functions will be bounded between 1 and -1. And if we go far enough to the left or far enough to the right, they will reach those extreme values. So these you could think of as basis functions. And then in the last stage, we're going to take a linear combination or an affine combination of such basis functions. And we've similarly sampled random parameters from the whole set of parameters to see what do the score functions out of this hypothesis space look like. And here are some example draws. So you can see they are quite expressive. They seem to be able to hit a wide variety of functions of X. Right. Okay. So the question is, if this is our hypothesis space or some samples from our hypothesis space, how are we going to find the right hypothesis to fit some training data? And at this point, we know exactly how to do that. We have all the machinery from the course, which is exactly what we'll use. And the primary difference is, instead of taking an argmax over a hypothesis space of linear functions or kernelized linear functions or trees or whatever it is, we're going to do it over the space of neural networks, which are parameterized with a lot of parameters, but they're parameterized just as many of our other hypothesis spaces. So let's go with the empirical risk minimization approach. For the model that we're dealing with, there's 10 parameters. And we could do square loss and look for the set of parameters that minimizes the square loss, per usual. All right. So question is, do we have the tools, do we have the machinery, the optimization machinery to find theta hat? So what would we need for that to be the case? Yeah, okay. So if the objective function is convex, then we have a hope to find the minimum by what techniques, for instance? Yeah, so gradient descent or SGD, some gradient method, is applicable if the objective function is differentiable or differentiable almost everywhere. So we could take a subgradient, for instance. So it's at least continuous and differentiable except at certain points. And so neural networks, certainly the one we've defined, is differentiable. Certainly differentiable everywhere if we use the tanh activation function, and we only have certain issues with the ReLU at the kinks. All right. So, but what you pointed out is that those methods, we're comfortable using those methods when our objective function is convex. And neural networks are not convex. So we gotta look. So we don't have the tools in some sense to find the minimizer because this is not a convex function, so we don't know what to do, but it turns out what we can find, a local minimum, is good enough. So As we pointed out, this is differentiable, so we can use gradient-based methods. It's not convex, so we're hoping we'll at least get to a local minimum, and in practice, this seems we get very good success with neural networks, so that seems sufficient. So one interesting thing about neural networks is that they have very good approximation properties. Remember back to maybe our second lecture, we talked about approximation error and estimation error. And approximation error was, there might be some functions that there's nothing in our hypothesis space that can get close to it, right? It's just too complicated. The true Bayes prediction function is too complicated, and our hypothesis space is too simple, and we're going to have some gap in performance because of our hypothesis space not being expressive enough. But it turns out we can make a neural network arbitrarily expressive in a certain sense. So approximation error should not be a limitation for neural networks. We'll give a theorem related to that. But first, let's look at some illustrations. So for the specific neural network we designed for our regression problem, the 3 hidden nodes with the tangent, hyperbolic tangent, let's look at how it does on some training data. So in this graph, the blue dots are training points, and the red line is the fit, the neural network fit, and you can see it pretty much nails it. These other dashed lines, what would those be? Well, okay. So the other dashed lines are the outputs of the hidden nodes, the 3 hidden nodes as functions. So each of these is a learned, corresponding to a learned set of parameters to determine that hidden node, that feature function, that basis function. All right. Here's a sine wave. Again, fits it perfectly with different basis functions. A v, pretty close. Misses it a little bit down there. Here's a step function, which it approximates pretty well. The point is that these can approximate functions quite well, and we only have 3 hidden nodes. So that's potentially an appealing feature. There's one thing a little bit tricky about this, though, I think. So this is like something like a y equals x squared sort of thing. What would happen if we extended the graph far left or far right? To the left or to the right? So yeah?
Not go up.
Yeah, this red it can't possibly keep going up. So eventually it's going to do very poorly. How do I know it can't possibly keep going up? Because the basis functions, the tangent, are bounded between -1 and 1. So we're only at the end of the day taking linear affine combinations of these bounded functions. So it can't go off to infinity like x squared does. So I thought that was a little bit sneaky, the way it looks perfect in this picture. Anyway, okay. All right. So there's a really nice theorem relating to these neural networks as we've described them, multilayer perceptrons. So in words, what the theorem is saying is that for a huge class of possible activation functions, basically you can use any function that's not a polynomial. So you can't use linear, you can't use x squared, but you can use hyperbolic tangent, you can use ReLU, you can use sine, cosine, x, whatever. And so if we have a valid activation function, then a neural network with just one hidden layer, possibly a huge number of nodes in that layer, but in any case, just one hidden layer, we can approximate any continuous function arbitrarily closely on any kind of compact set. So you could think of a bounded set in RD or something. So the hidden gotcha in this is that the number of hidden nodes you need can be exponentially large in some sense, so impractically large. But still, it's at least somewhat satisfying that, perhaps it's satisfying that you can, there's no function you can't approximate with enough hidden nodes. All right. this just spells it out in some more detail. The sense of good approximation that we mean is that if f of x is the output of our neural network, and capital F of x is the neural network output, little f of x is the function we're trying to approximate, then at every point x in the compact set, the gap is at most epsilon for any epsilon. All right. Yeah, one thing that they point out that's important in the proof is that you need this bias term. So if you just have linear combination of the inputs without the bias, you have issues. And this is actually not so difficult to see. Imagine your activation function were something like sine of x. So you know, whoops. So this is 0. Okay. That's not sine of x, sorry. Yeah. All right. That's like sine of x. 0. All right. So this is an odd function, right? So that means sine of x, sine of negative x is equal to negative sine of x. So it's kind of, you could reflect it around the origin. It's symmetric about the origin. And if that's our activation function, and we're taking just kind of combinations of sine of x, so if we only had a linear function of x, so I claim that f of x is always an odd function, just as sine of x is, right? If we plug in negative x here, the negative comes outside. And so f of negative x is negative f of x. So what's the point here? The point is that if you use, if you don't have a bias term, an offset term that you can adjust, then you can only model functions that are odd, right? And there are lots of functions we want to, only model functions that are symmetric about the origin. So, all right, so that's regression with multilayer perceptrons. Let's talk about classification. Make sure we can do both sides. Yeah?
So when you mentioned that this is equivalent to gradient boosted trees where you find the weights on the basis functions?
Yeah, I claimed it comes to a same form as gradient boosted regression trees, yeah.
But the function here is the same, the input changes.
Say again?
The functions, the basis function is one and the same thing. It's the same activation function, just that the input is changing. So isn't this a different thing than gradient boosted regression?
Yeah, I mean, it's this. They are related just to the extent that kind of you're learning a set of functions, in this case h1 through hn or whatever, and you're also learning you're ending up with a linear combination of those functions. So one can interpret that as learning features for a linear model. That's the similarity that I wanted to make. Yeah. Well, but of course, I mean, for gradient boosted regression trees, you usually use regression trees as your basis functions, whereas here we're using these smooth basis functions, tanh or relu or something like this, or at least continuous. Whereas trees are piecewise constant and discontinuous. One other thing, I pointed this out during the tree lecture, but I'll point it out again, is that here we're able to learn the features and the linear combination of those features in one fell swoop using gradient methods. For the gradient boosting regression trees, we couldn't do it that way. We had like a two-stage algorithm because we couldn't differentiate. We can't differentiate with respect to parameters of trees. Trees are not differentiable in that sense. So we had to use some other way to figure out the basis function that we added in each round of gradient boosting. Whereas here, it's actually much easier, where we just write down the entire objective function. The whole thing is differentiable with respect to parameters, including learning the features. So gradient methods work kind of out of the box. So in some sense, neural networks are much simpler. They were invented much earlier also. All right, should we move on to classification? That's the other major, probably the more common use for neural networks compared to classification, regression. But let's start with, it'll go much more smoothly if we're really fluent in our multinomial logistic regression setup, which we talked about a few weeks ago. So setting, we're going to have an input space of RD and K classes. And the goal is for any input X to produce a distribution on the K classes, right? And that would be like a soft classification. If we wanted a hard classification, you would just take the class that had the highest assigned probability for the given input X. A distribution on a discrete set of categories is called a categorical distribution, or sometimes multi-newly distribution. And we can represent it by a probability vector of length k when you have k different classes. So if it's theta, the entries of theta sum to 1 and they're non-negative. That would be our probability distribution that we'd like to produce for any given x. So the way we do it in multinomial logistic regression is the input x gets mapped to k score functions, if you will, and each of those scores, one for each class, is a different inner product of x with some parameter vector. So we have one parameter vector for each class, w1 through wk, and so each of those gives us a different score. We would classify by whichever score is greatest if we want to do hard classification, but if we want a probability vector, do you remember how we're going to map these scores into a probability vector of theta? There's a function we talked about. Yeah. It's called softmax. So softmax function takes k scores, or arbitrary reals, and sends it to a vector theta. By this function, we simply exponentiate each of the scores that make sure that that the result is positive, and then we normalize to make sure they sum to 1. So that guarantees that this vector is representing a probability distribution on the k categories. All right. So given some scores, we can get probabilities. That's great. And then how do we learn? Well, we want to go in the direction of likelihood, maximum likelihood, which is to say, given the training data, adjust all of our parameters so that the training data we get has, the labels we get have high likelihood overall. So for a given training example xy, the predicted probability for y, if y is like a class index, so y is a number 1 to k, it's discrete, then the softmax of the scores gives us the probability vector, the whole distribution. So the probability of the particular class y is the yth entry of that softmax vector. Is that clear? Because softmax returns the whole probability vector, so we're choosing, if we want to know the probability of y, say y equals class 3, then that's the third entry of the softmax vector. Right? Great. So then we can write down the log likelihood of the training data. And the objective function would be to maximize over all the parameter vectors of the softmax. That gives you the distribution, and then we subscript it by yi, the label for the ith example. That gives us the probability of the predicted probability of the label that actually occurred with the training data. We want that to be large. Then we sum the logs of those and maximize. So that would be maximum likelihood for multinomial regression. All right. So that's great. This is a linear method. We want to get neural networks in here somehow. So do you see where a good entry point might be to get some neural network action into this picture? Yeah.
Multiple output nodes.
Multiple output nodes. Okay, and each output node would be?
The sort of
Yeah,
equivalent
the score.
to a WI XI.
Very good. So instead of having these WIX's, we would swap out each of those with the output of some multilayer perceptron. That's right, that's right. Okay. So in this linear case, the functions we're maximizing, the function is concave, straightforward to optimize. So that's very nice if you want to do multinomial logistic regression. All right, so now let's go to the multilayer perceptron approach to classification. So as was suggested, the key change is rather than having these k linear score functions, we use k nonlinear score functions, f1 through fk. And in that case, the predicted probability has the same form. We just swap out our score functions for nonlinear f's instead of these linear functions. And we look, just as before, we could do maximum likelihood. We could use gradient boosting for this. All right, we talked about, we didn't specifically talk about multinomial, but that would be an interesting exercise. So we can learn the FIs as ensembles of regression trees. But today we're going to talk about using multilayer perceptrons for the F. This won't be convex or concave, but the gradient methods will kind of give us a good enough optimum. So let's look into some details. So we're going to think about producing a vector of score functions, a vector of size k for the k classes. And let's fix sigma to be some activation function, something non-polynomial, because we know that it has some theoretical properties. And for simplicity, let's say our hidden layers all have m units. All right. So let's rehearse this a bit. Let's work it through. Let's write down kind of what the form for these expressions would be. So the input is RD. So let's just write X is in RD. And that feeds into the first hidden layer H1. All right. And what kind of parameters do we need for figuring out the output? Let's call that O1 for the first output. So let's say O1 is equal to what function of X? Yeah, there's going to be some activation function, sigma. We're going to have some affine transformation of the input. How many should we have? An affine, what's the output dimension of the affine transformation? What's the output dimension? What dimension is O? Do we specify that?
Okay.
Take all hidden layers that have m units. So we're on the first hidden layer. So it needs to produce, for an input of size d, we need to produce a vector of size m, because that's the output of the m hidden units. All right. So let's start with an affine transformation of the input, right? Because every layer starts with an affine transformation and then runs it through a nonlinear transform. So I'll write down like this. Some matrix W1 times X plus some bias. All right. So what dimensions is W going to have? All right. So X is, we'll say D by 1. We want the output to be M, so W must be M by D. Yeah. MB Yeah, m by 1, great. Now sigma, we really define sigma to operate on a single scalar and output a transform version of that scalar. So in this notation, what you should think about is sigma acts on each entry of its argument individually, and so we'll write it this way for convenience. All right. So this is a bit of a compressed version of the computation graph. We could also have written it like this. x1 all the way down to xd. So that'd be d input nodes. And then kind of all the different interconnections into n hidden nodes. So h1, how many hidden nodes? M hidden nodes, all the way down to hm. And then we'll see what happens next. So in this version, I was kind of forcing you to think in terms of vector-valued inputs and vector-valued outputs. We can also go back to kind of the expanded version where we have every node corresponds to a single scalar. We'll go back and forth between the two. All right. But is this clear on the first hidden layer? Okay. All right. So let's add a second hidden layer. All right. All right. That's going to give an output 2, also an RM. All right, so what's the form of O2? Yeah, W2. O2 applies to O1, so the output of the previous layer. Great. So what are the dimensions of this W? M by m, because its input is of size m, because it's the output of the previous layer. And so this is a square matrix. Good. All right. And then in the last layer, we have to produce a single value, and typically the standard is that in the last layer, we don't have any nonlinear transformation. So I think I just can refer to the slides for that. So this is so we wrote down the second hidden layer, but all the hidden layers after the first are the same as long as we have the same number of hidden nodes. The first one was only different because it had to account for the fact that the input dimension was different from the output dimension. But after that, we're using the same input and output dimensions. So the final layer is typically not with a nonlinear transformation, so it's just an affine transformation of the last output. And again, we have a dimension change to get the k classes that we need for this multiclass, the k-score functions. Any questions on this setup? So we have the input, then we have some number of nonlinear computation layers, and then the last thing is an affine transformation, which is a linear transformation to produce a vector in Rk, k-score functions. All right. So this is kind of what we're predicting, and now we have to add on, to finish it up, we're going to have to add on the loss function, or the softmax, and then the likelihood loss. So one way to think about the full neural network is it's the composition of all these layers, or all these functions, h1 to hd hidden, and the final activation layer, the final affine transformation layer. And we want to maximize this conditional log likelihood where f is now the neural network, and the neural network is outputting a vector in Rk, the k-score functions. We run it through softmax, which converts the k-score functions to a probability vector. And then just as before, we subscript to find the entry corresponding to the training data, etc. I am missing one thing here. You see what I'm missing? It's a typo. For this to be the objective function. I could fix this in two ways. I can either change this sum to a product, or I have to put a logarithm in there, right? Because the likelihood for theta for the training set is the product of the likelihoods of the individual training examples. Softmax subscript depth gives us the probability, but we're doing an average here, so this better be log probabilities. Right? So there was an interesting question over the break, a few of them, but one of them is ReLU is convex. If we kind of compose all these ReLU functions of affine transformations, are we really not ending up with a convex function? And let's look into that. Let's look into an even simpler version where we have no nonlinear transformation at all. So x maps to, let's do h1, and then maps to h2, where h1 is w 1x, h2 is w2, said h1, I really want to say output 1 to be consistent, sorry. All right. And then let's just say the final output. Well, that's enough, really. It's linear already. All right, so if our output f is equal to O2, what has the neural network done for us? All right, so is this a convex function? Thoughts? There's, okay.
Linear in x.
It's linear in x, absolutely. F is a linear function of x. Linear functions are convex. It's a convex function of x. Okay.
It's also a linear function of the parameters.
What?
It's also a linear function of the parameters.
Is it a linear function of the parameters?
Is it because each one is a separate parameter, each double?
Yeah. So this is a highly nonlinear function of the parameters.
Depending on where you say your parameter is.
The parameters
Yeah.
are every entry of the W matrix.
If you combine them together, it becomes just one matrix there. Then it's become just typical linear regression.
Correct. So with the parameterization as a neural network, you have separate parameters in each matrix. And when you multiply this out, this will not be a linear function in these parameters. But you recognize that the expressivity of this function class is equivalent to if you just had one matrix. Because it's just, as pointed out, was linear functions. So if you were to reparameterize it, then of course it's trivially linear in the reparameterized a single matrix. But in the neural network parameterization with different layers, it's not, even though the final function is linear, it's not convex in the parameters. And of course, this is just a simplified case of what we would actually use. What you'd actually use is you'd throw a nonlinear transformation in each step here. So if you put in a ReLU, you know, it's not convex in the same reason, for the same reason that it's not convex in the simpler linear case. Yeah, that's a great question. Is that clear? It's a bit subtle point anyway. So these networks have potentially massive capacity, which is to say they can fit almost any training data if you make your network large enough. What can we do? So we already have the tool for this. This is regularization. And can you regularize neural networks in the same way? Sure. So the regularizations we've discussed so far are L1 and L2 regularization primarily. And people, in fact, do use these in neural networks. In the neural network literature, it's sometimes called weight decay instead of L1 and L2. Here, for instance, F is parameterized by two sets of weights, W and V, like the network we had earlier. And this is your regression loss function. Just add in L2 norms on W and V, and this is your new neural network objective function, your weight decayed objective function. Certainly carries over to neural networks. But neural networks have come up with some new stuff. Another thing to think about, and you can use this in any model, is when you have an iterative optimization method like gradient descent, stochastic gradient descent, you might consider doing early stopping, which is to say, don't go all the way till your algorithm converges. You can stop early if you think your performance is starting to get worse. And there's a particular recipe. Yoshua Bengio has this in a paper I referenced below. Because the question is, if you're monitoring your performance on validation data as you go, there might be some noise to it, right? So if it ticks up a little bit, do you stop right away, or how do you know when to stop? So here's a recipe. You're checking your validation set every once in a while. Don't stop immediately when the performance gets worse. He suggests using this notion of a patience parameter, which is a number of steps you're going to keep going beyond the point where your validation error last improved, right? So you're going for a while, you hit a new best on validation error, and you go another step and it gets worse. Don't stop yet. Keep going, patience number of steps at least, to see if you might hit something that's still better. And then his suggestion is starting with some initial value of patience, say like 10,000 steps. Keep every time you hit a new minimum, you increment you make your patience parameter longer. So if you've gone for 100,000 steps and you got a new minimum, go for some kind of make your patience parameter longer by something proportional to how many steps you've already taken. So this is completely heuristic. Seems to help.
Is there also trade-off on the competition? Can you parallelize more?
So that's a good question on parallelization. So you can't parallelize layers, obviously, because they're sequential. You can parallelize nodes, and some people try to do that. I don't think that's the more common type of parallelization these days. The more common type of parallelization we spoke about in lab was breaking up your mini batch across multiple machines. So that would be called data parallel, where you compute parts of your mini batch and then you combine them to take one step. Yeah, but there certainly is work where you send like half the nodes of a certain layer to one GPU and half the nodes to another GPU and parallelize in that way. All right. There's one really cool thing you can do with neural networks very easily. You can do this with other, I'm getting at what's called multitask learning, and you can do this with other frameworks as well, but it's very simple and nice with neural networks. So the idea is that you have a neural network and you have multiple outputs. We've already spoken about multiple outputs in the case of multiclass, but here the idea is that the outputs are really about different problems, about different things. But they are related in the sense that they're on the same input space. So for instance, object classification your input is a picture with pixels, and your output is there a dog in this picture, yes or no? But there's another separate binary problem. Is there a cat in this picture, yes or no? And is there a giraffe in this picture, yes or no? And this is not a multi-class problem. It's called a multi-label problem because you can have multiple of each of these in the problem. So it's really 3 separate binary problems. And you could build a neural network that has an output for each problem on it, and you could train them jointly. You only would have to decide how to weigh the losses of each of the problems, and usually you would maybe assign uniform loss to each of them to combine and get one combined objective function. So why would you want to do that? The idea is that if we think about a neural network as learning features, it would be useful to combine tasks into the same model if you think that features that are good for one may be good for the other. And so you can use all your labeled data related to dogs to help you build your model for predicting cats, because the features that it's learning to help predict dogs would also be useful to help predict cats and vice versa. So in the vision example, it might be like I described, the low-level features like learning edges and learning angles. It has nothing to do with whether you're looking for dogs or cats. And so the more data you have to help with those low-level tasks will pay off for both of your tasks, both cat and dog. So that can be quite useful if you have multiple tasks to solve. You can also think about, what if there's only one task you have to solve? You could still use this approach. And here, maybe you really don't care about cats. You only care about dogs. Fine. But if you have labeled data for lots of different animals, lots of different objects, you can go ahead and put those in as extra tasks. And then in this case, you might call them auxiliary tasks. And they're not there because you care about those tasks per se, but you hope that this will give additional data to help it learn good features. Maybe you only have a limited set of labeled examples for dogs. I don't know, call it 50,000. But if you combine all of your objects, you have 1,000,000 examples, right? And so if you used all these examples together, you will have potentially be able to learn much better low-level features, which would benefit all of your tasks. Is that clear? Okay. And then here's a good trick. Suppose there is no obvious auxiliary task that you have labeled data for. What you could do is you could take your data from that one task and create new tasks out of it. So here's an approach. So take an input feature from your input data, change its value to 0, and then make the output the prediction problem trying to predict that particular feature that you zeroed out. All right? Is that clear? So if we have an input example, so for problem 1, well, we have one problem we're interested in. And maybe we have x1, x2, x3, so a three-dimensional input vector. And this is mapped to, I don't know, yes, it's a binary classification problem. Now we make an auxiliary example, auxiliary problem 1. In auxiliary problem 1, we erase the first coordinate and try to predict it back. So the input is then 0 or some other default value that would make sense to you, x2, x3, and we try to predict x1, say as a regression problem or as a classification or whatever makes sense. And you could repeat that with x2 and x3. So the hope here might be that by training it to predict its own input features, it might learn how to be more robust to errors in the inputs, or it might understand different relationships between the input features better. In any case, it's something that could be interesting to try. Is that clear how this auxiliary problem works? These auxiliary problems? Okay. And the ultimate goal is by adding these auxiliary problems or extra tasks, it will learn better hidden units because the underlying hypothesis is that hidden units that are good for one problem are probably good for similar related problems. And by adding more problems, you're essentially adding more data. And more data will help you learn those common features.
Is this the same network or is this?
Same network. That's the thing. Because it has this, the key piece is that it has to have the same input space and action space. Yeah. That's right.
But like in the first one we are doing like a classification, here you're doing regression.
I'm doing?
In the first one you're doing a yes or no classification, here you're doing regression.
Yeah, crazy. So, okay, so right, it's not the same output space. Same input space though. So my objective function might be like, I have my classification loss, and then I add lambda times my regression loss for the auxiliary problem. All right. Okay. All right. So especially in the earlier days of neural networks, not many people had the resources to train these neural networks. And so even now, in fact, some of the networks that, for instance, do object recognition on the ImageNet data set can take weeks to train on a standard GPU configuration. It's really expensive in terms of compute power. So what people tend to do is reuse networks that have already been trained. They're called pre-trained networks. But even before that, one cool thing to do is think about using neural network hidden units as features in a linear model. So an example of that that's quite successful is Overfeet is a neural network that was trained on this ImageNet classification, huge resources to train, and if you extract the hidden units as feature functions and then retrain, use those as features in a linear model, you can do excellent, you can do quite well very quickly because linear models are quite fast to train. So there's this paper that kind of made this point on reusing these neural network features. We kind of made the same point for trees. Trees is like is a way to make feature functions. You can think of it that way, where every leaf node is a nonlinear function of your input. So it's the type of thing that you could plug into a linear model as a nonlinear feature. Clustering. Sometimes I like to think about clustering as a way to generate nonlinear features of my input space. Here's another kind of cartoon picture, which is, I don't know, kind of folk wisdom. There's a lot of folk wisdom in neural networks. So what this is, the point of this is that deep learning can leverage the huge amounts of data that we have these days just much better than our traditional methods, simpler methods. So when you start to get billions of examples, the older algorithms kind of plateau, whereas deep learning can keep improving. I don't know. The science to this is kind of empirical observations. All right. And the question was, GPUs, how do those play in? And you're right, it's a serious question because the neural networks people use these days on GPUs can typically take 2 weeks to converge. On traditional box of CPUs, like 48 cores, it could run for almost a year to achieve the same level of performance. So what are GPUs doing? They're just massively, they have like, it's kind of the equivalent of having, order 10,000 cores working on your matrix vector multiplications as opposed to 50 or something like that. So it's kind of gives you massive parallelization. Yeah.
So, as a software engineer, 2-week convergence sounds rough. Where like 2 weeks later you have to check your results. Is there any way to like pare down your problem to test it before like you spend 2 weeks running something that might be problematic or?
Yeah, so a few things. One is not all neural networks are that slow. These are kind of like state-of-the-art types of things. But two, what people usually do is they'll take a network that's already been trained on some problem similar to theirs, so they can use the same, they take literally the same network, and then it's called fine-tuning, where you'll replace the original training set with your own training set, and then you'll continue training with the new training set, and then things go much faster. It could be like a couple days instead of a couple weeks. But yeah, the compute power required to train these large neural networks is quite large. Yeah. Okay. All right. So that's what I wanted to say for kind of an overview of neural networks. Neural networks are used to solve a lot of problem types that we haven't discussed in this class, so I've left those out. And I'll come back to them, not to them per se, but I'll try to mention, if we have some time, the other problem types at the end of today.